Hello, welcome to the 16th video on our linear algebra series. So today we will continue with the 7th chapter, and this is 7b of Axler's book. The title is Spectral Theorem, and we will discuss it over our two fields, the real and the complex field. So last time we have a joint of a linear operator denoted as if you have an operator T, we have the adjoint is just T star. And then the conjugate transpose of a matrix where basically we are interchanging the rows and columns and then getting the conjugate. This is defined over C. And then we define self-adjoint operators and normal operators. Today, we will start with our spectral theorem. So let me do it on the next board. So recall, we have a diagonal matrix, say lambda 1, lambda n, and then all the rest is 0. This is called diagonal matrix. And then what? From we also recall that if we have a linear operator, on V as a diagonal matrix with respect to bases, as diagonal matrix representation with respect to bases, if and only if this basis here consists of eigenvectors of our operator T. And then, of course, if we have a diagonal matrix, we have somewhat a nice operator. So we say that a nice operators are those with diagonal matrix with respect to orthonormal bases. And the goal for this chapter is, of course, we have this diagonal matrix, and then this orthonormal basis here consists of eigenvectors, vectors of our operator T. So the goal today is to characterize these nice operators. So nice operators. And then we will do this in the setting of F, which is our complex number, and then F wherein our F is the second one is real numbers. In the case in complex numbers, we have normality. The normal operators are those nice operators, and then for the case of F being real numbers, those nice operators are those self-adjoint operators. All right, let's begin with an example. This is just to get a grasp of it. So suppose we get a linear operator T in C2. Complex numbers, 2 copies of it, and T has matrix M of T given by 2, -3, 3, 2. And then this is with respect to the standard basis. And you have to verify this list, one I, and then 1 was over 2, and then the second one is negative I 1 over 2. So of course, this is something like I over 2, and the second component is 1/2, and then negative I over 2, and the second component is 1/2. So let us consider this as our V1 and our V2. This list is an orthonormal basis, orthonormal basis of C2 also. And then our claim here is this V1 and V2 are eigenvectors of T. So you can verify this, but that is T VI is equal to lambda I VI. And then with respect to the basis, to this basis, so when I mean this basis is this basis, we have our matrix of T is given by 2 plus 3i and 0, and then 0, 2 minus 3i. So this is a diagonal matrix. Now, let us check the PV1. This is just 2, negative 3, 3, 2, and then we get I over 2 and 1/2. So this is your V1, and this is our matrix of T. So you get here, this is 2 times I over 2 minus 3 times 3 over 2. And then the second component is 3 I over 3 times 3 over 2, 3i over 2, and then plus 1/2. And then this is, of course, we can 2 plus 3i, and then I over 2, and then 1/2, which is just lambda 1 V1. So here we verify that your V1, V1 here is an eigenvector associated to this eigenvalue 2 plus 3i, which is appearing here. And then the other one, of course, I can verify the following: TV2, this is just 2, negative 3, 3, 2. And then what's the V2? V2 is negative I over 2, then 1/2 will give us 2 times I over 2 minus 3 times 3 over 2. And then the other one is negative 3i over 2, then plus 2 over 2, which is just 2, and then minus 3i, and then 1, negative I over 2, and 1/2. You may pause this video and verify this one. So this is our lambda 1, and this is our lambda 2. So here we have a diagonal matrix wherein the diagonal is composed of the eigenvalue, and then the basis, the matrix with the matrix which is diagonal, and then the diagonal being eigenvalue is with respect to an orthonormal basis, basically consisting of the eigenvectors of T. So this one is eigenvector number 1, eigenvector number 2. So that's it. So now I think we have the grasp of what's going on. Let us characterize the nice operator on complex inner product space, and then we call this first resolve the complex spectral theorem. Okay, let me write this out. Suppose F is your complex numbers and your linear operator is this V is a inner product space over C. The following are equivalent, and the following are equivalent. Number one, letter A, T is normal, and then letter B here, V has an orthonormal. Basis consisting of our T, letter C, T has a diagonal matrix with respect to some orthonormal basis of our P. Before proving this theorem, we have to recall the following result from previous discussion on characterization of diagonalizable matrix. So this is a theorem before. This is the characterization or properties, or I mean equivalent conditions for diagonalizability. So we have T, a linear operator, on V, and here I'll just state two equivalent conditions. T is diagonalizable, and then the second is V has a basis consisting of so this is our previous result, and now we are ready to prove this theorem. Okay, let us only show A implies C and C implies A, because B implies C is from the theorem above. So here we have diagonal matrix, and then we have an orthonormal basis with respect to that, and that is obvious with the other characterization here. In 7 point, I think it's, let me check, 5.41. Equivalent conditions to diagonalizability. So here, being diagonalizable, we can write it as a diagonal matrix. Then we have a basis consisting of eigenvectors of T. So follows from the previous, the recalled theorem here. Okay, let's go back to A implies C, and then this is what we want to show. And then C implies A. Okay. All right. Now, let us suppose C holds. Then, if C holds, we have a diagonal matrix. Say M of T. With respect to some orthonormal basis. Of T. Okay. So this matrix is diagonal. Then your matrix of, of T star is just the conjugate transpose of your MT. And what can you say about conjugate transpose? If we have a matrix which is diagonal, its conjugate transpose is also a diagonal matrix. This M of T star is also diagonal, a diagonal matrix. And we know that the diagonal matrix commute. So we get T star T is T star T star. That is T is normal, and then that means A holds. Okay, easy. Now, suppose our A holds. Then if A holds, we have T is normal. Then recall the following theorem. Shor's lemma. Not Shor's lemma, Shor's theorem, which says that if we get a finite dimensional vector space V and T a linear operator on V, then T has an upper triangular matrix with respect to some orthonormal basis of B. This is the theorem that we need. So suppose now that we get an orthonormal basis. We have by Shor's theorem, there is an orthonormal basis with respect to T, to which T has an upper triangular matrix. So here we get E1 to AN orthonormal basis. And then we have matrix T with respect to this orthonormal basis. It's given by your A11 up to A1N, and then here AN and here we have everything here is 0. So this is a upper triangular. And then we want to show that M T is diagonal. Okay, how do we show that? So from the matrix above, here we get T E1 squared is just A11 squared. Okay. And also, we get T star of E1. The norm is just given by if you have this in the reverse direction, they get here like this one will transfer here, and then with respect to E1, we get A11 squared plus A12 squared, and then up to A1N, no, A1N squared. And then T is normal by assumption. Thus, TE1 is just equal to T star E1. Okay. This is true by our 7.20 which states that if we have our normal operator, then the norm of t applied to b is just equal to the norm of t star v. Okay. All right. Okay, we can apply this over and over again until we get only the diagonal will be non-zero. So this means these equations here, let me put this in different color, this one and this one will have all the entries in the first row of the matrix. This means from these two equations, about we get all entries on first row are 0 except possibly A11. Of course, there's a possibility that A11 is non-zero. Now we can apply this again. Also, we have T E2 is just T star E2 squared norm. And then we have T E2 is just a 2 squared, a 3 squared up to a 2n squared. And then using same argument, the second row is composed of zeros except possibly at the place of A22. So you continue this. If you continue that, what you get is what? If you continue this, you get you will get the only diagonal entries are possibly non-zero. So that means this gives us our C-holes. That is what a C-hole. We have a diagonal matrix representation with respect to some orthonormal bases. So this ends the proof of the complex spectral theorem. All right, now we go to the second part, which is the real spectral theorem. So basically, what complex spectral theorem tells us is the following. If we have for our complex inner product space, those nice operators are those operators which are normal. That is, T star T is just T star. That is the adjoint with its the adjoint of linear map with itself commutes. So if that's the case, we get a diagonal matrix representation with respect, of course, the important term here is the orthonormal basis. Okay, now we characterize the nice operators for a real vector space. Before getting to the theorem, let us build some theory first. Okay. So here we will start with some preliminary results. So you recall that if you get x squared plus bx plus c, this is equal to x plus b over 2 squared plus c minus b squared over 4. This is greater than 0 if your b squared is less than 4c. And here x is a real number. So this is the result from our high school math. So in particular, this is, if this is 0, this is invertible. Real number. If you plug in x, arbitrary x, and then b squared minus 4ac for some b and c, which satisfies b squared is less than 4ac, you get here an invertible real number. So now we will use this concept by replacing, instead of x, we will replace this with a linear operator. Okay, let me state this a proposition, or in this case, as I always use theorem. Suppose here that we get a linear operator on V is self-adjoint. And you get your B and C are real numbers such that your B squared is less than 4C. Notice that we don't have A here because we just consider the monic polynomial. That is, your A will be is just 1. Then your T squared plus B T plus C times the I is invertible. So here is the proof. Let V be a non-zero vector and T be a linear operator. This is self-adjoint. Okay, then let us expand. Let us consider the inner product of T squared plus BT plus C times I apply to V. V is just T squared V plus B T V here plus C V. Inner product. So here since our T is self-adjoint, we get T here. V is just V plus B, and we get here V plus. This is why T is adjoint this inequality. Then we get here C times V squared is greater than or equal to B minus B TV V plus C V squared. So it's because of Cauchy-Schwarz that is UV here. This absolute value is less than our absolute value U, norm U times norm of V. And then we will now invoke this part here will be equal to your T of V minus the norm absolute value B, and then V squared over 2 squared plus we get C minus B over 4 times the norm of B squared. And this is non-zero, greater than zero by our claim earlier. This means that thus your t squared b t plus ci v is not zero. Thus, because it's non-zero, t squared plus vt plus ci is injective. And since we are in a finite dimensional vector space, hence we get bijective, or that is invertible. As a result from previous. So if we have an operator with this form, we get a positive, an invertible operator. When we have an invertible operator, then we can always get its inverse. Okay, we know that every operator, self-adjoint or not, on a finite dimensional non-zero, non-trivial vector space has an eigenvalue. So because it's an eigenvalue, then we have the following result. Let's write this out. If B is not the trivial vector space and T is just operator on B, self-adjoint, then here T has an eigenvalue. All right. So we now prove this. So because you're dealing with a spectral theorem in real inner product space, we assume V is real. Inner product space. And then n be the dimension of our vector space. Choose our arbitrary element V in our vector space V, which is, of course, the nice one, not zero. Then your V here, TV, T squared V up to T to the NV is can't be linearly independent because there are here n plus 1 vectors and our V has dimension n. So we can write 0 as the linear combination of up to not all 0 or 0. So we can look at this as coefficient of polynomial. So look at polynomial as we have before. So we get a 0 plus, instead of t of x1, we get t of v, we get just a1x plus anx to the n. Okay. And then we can write this as follows. We have c, and then x squared plus bx plus c1, and then up to x squared plus bmx plus cm, and then multiply with x minus lambda 1 up to x minus lambda m. Your c here is non-zero. And what else? C non-zero, your bj, cj, and lambda j are real. and your bj squared is less than 4cj. And then we have m plus m, of course, should be greater than 1. And then the equation holds for x in R, real number. Then 0 here can be written as a0v plus a1tv plus up to an env. Okay, by a property of linear operator, we can put our v outside. So a0 and then I plus a1t plus up to an t to the n, and then multiplied by v. All right, now we can write this entire thing as c, and then t squared plus b1 t plus c1 I up to t squared plus bm t plus cm I, and then t minus lambda 1 I, and then t minus lambda m I. Okay, times, of course, v. Now we have t squared plus bj t plus cj I are invertible. They are invertible. And c non-zero, then we can divide both sides with them. They have their inverse. Thus, your equation above implies your m must be greater than 0. And your what? Your 0 is just equal to t minus lambda 1 I up to t minus lambda m I times v. Hence, then, okay, hence your t minus lambda ji is not injective for at least 1 j. This means t has an eigenvalue, which is what we need to show. The next result is preliminary to the main result for this meeting. Let me say this as a remark. So if U is a subspace of V, of our V, and U invariant under T, then U is invariant under T2. And in fact, we will show that this self-adjoint requirement can be replaced with normality. So here I claim that self-adjoint is stronger than normality. I think I will be giving this in our exercise. Of course. Okay, let me state this as a theorem, and then I will leave the proof as an exercise. I will just outline the first one. T, a linear operator on V, self-adjoint. U is subspace of V that is invariant under T, then the following holds. U is invariant too. Under the same operator T, and then we get T restricted to U is also a linear operator on U. Is also self-adjoint. And C, T restricted to U. Perp is a self-adjoint operator on U perp, or the orthogonal complement of U. I will prove the first one, and the rest will be left. So we will prove A. So suppose we get a vector in U perp, and then U in our U. Then because T of B and U is just V, T of U. This is being self-adjoint. This is equal to 0. So this first equality is being self-adjoint. U of T. And the second equality, because since U is invariant, and then T of U is in U, and V is in U complement, orthogonal complement, to get their inner product is 0. This is if B is in the orthogonal complement and U is in the UV is in the orthogonal complement of U and U is in U, then we have our equation holding, because that means that T of V is also in U perp. Thus, U perp is invariant under T, completing the proof of A. So, okay, let me write that out. Because this equation holds for any U in U, we have T of V is in U perp. T, and thus here U perp is invariant under T. Okay, because TV, U here is in U, TV is, if their dot product is equal to 0, that means your T of B is also in the orthogonal complement of U. That means it's invariant under T, and then A holds. So your B here is easy. So for B, you get the inner product of T, and then apply it to U, V. This is just T of U, V. It's just U, and then T of V by self-adjoint condition, and then this is equal to U, T, restricted to U of V. Thus, your T restricted to U is also self-adjoint. Your C is same by replacing U with U. Perfect. Now we are ready for our real spectral theorem. So for real inner product space, the nice operators are those self-adjoint operators. Okay. The following are equivalent. Number one, T is self-adjoint. B, V has an orthonormal basis consisting of eigenvectors of T, and C, our linear operator T has a diagonal matrix with respect to some orthonormal basis of over V. Again, we will prove here, we will only prove let's see, C implies A, and then A implies B. We will prove C implies A, and then A implies B, and then B implies C. Here, B implies C is given, same as with complex. So here we will prove this part and this part. Okay, we have A, B, C, and then of course, this is already this. So now let's start the proof. Suppose C holds. If C holds, we get the diagonal matrix. C holds, then the diagonal matrix. Okay, let's. E has diagonal matrix. We are working with the real inner product space. Basis. A diagonal matrix is equal to its transpose. Hence, your T is equal to your T star, and thus T is self-adjoint. So we have C, then we get a self-adjoint. So A holds. Now, suppose A holds. Want to show B. So the method is in the dimension of our V. So if your dimension of V is equal to 1, then what? This is A is self-adjoint, then of course this is true. Because if we get a dimension 1, then the basis is just this is easily follows trivially. It's just a real number. Okay. The real number, set of real numbers. Now we have the hypothesis of induction. So assume this is our induction hypothesis for dimension of v less dimension of v greater than 1, and then greater than 1 and smaller than dimension of v. Assume that the dimension of b is greater than 1 and a implies b for what? For smaller dimension. The dim b here is your dimension of the original vector space. Okay. Let us consider an eigenvector of of course we normalize u so that its length is or norm is 1. So this is by normalization. Let us consider u the span of this vector u, the span of vector u. Then here u is one-dimensional subspace of v. So this is a one-dimensional subspace of v that is invariant under T, because here T is an eigenvector. Okay. So U is a subspace, so smaller than. So by our inductive hypothesis, by our previous result, then T restricted to the orthogonal complement is a self-adjoint operator on U perp. So of course, by hypothesis, there is an orthonormal basis for U perf. Because here U perf being U is a one-dimensional subspace, of course U perf will also be a subspace. What's our induction hypothesis? A implies B for smaller dimension. That is, let me go back. As a orthonormal basis consisting of eigenvectors. Okay. Consisting of eigenvectors. This is basically true because U perp is just a smaller dimension than B. And then applying our induction hypothesis, we get U perp has an orthogonal basis consisting of eigenvectors of eigenvectors of our operator T. Okay. T restricted to U perp. Okay. Now, okay, we adjoin this U to the orthonormal orthonormal basis of U per. So what do you get? Because this U is just a basis of our U, we have this one. Okay, you have say S here, and join U is a basis of our vector space B, consisting of eigenvectors of our T. Recall that this is also T restricted to U, and then this T restricted to U perp, this is T restricted to U, then we get the eigenvectors of T, thus completing A implies B by induction. So for we already have C. Okay. We have proved C implies A, and here implies B, and then C implies B implies C here is easy, as we have remarked with recalling our theorem on the equivalence of diagonalizability and existence of an orthonormal basis consisting of eigenvectors, and then diagonal matrix, and then being diagonal, we get our self-adjoint. So since we have our diagonal matrix, then this is already done. Okay, let's end this lecture with some remark. So if your F is C, then this spectral theorem gives your spectral theorem gives the complete description of the normal operators and B, and then a complete description of self-adjoint operators. So for our V, you just have by theorem, they are those with real eigenvalues. So if we have complex numbers, then we have characterization of normal operators, and then for complex inner product space, the self-adjoint operators are those operators with real eigenvalues, and then this is from the exercise that will be verified. Now, if your F is real numbers, the set of real numbers, then the spectral theorem has complete description of self-adjoint operators. For normal operators, on V here, we will do them soon. We will leave that for reading on, say, chapter 9. In this section, 9.34 of the book. Basically, it says that the following. for normal operator, there is an orthonormal basis of the vector space V with respect to which T has a block diagonal matrix such that each block is a 1 by 1 matrix or a 2 by 2 matrix of some form. It's just as like block. This relates to block matrices, which we will cover in the next weeks, or maybe no, or I don't know. Okay, that's all for real and complex spectral theorem. So for next meeting, we will consider 7 after spectral theorem. We will consider positive operators. Example of positive operators, we have isometries, and then after that we will go to the polar decomposition and singular value decomposition. So next will be positive operators. So example of positive operator is what? Square root, and then the other example is what else? And then we will go to isometries. So basically these are distance preserving distance preserving operator. So when say of distance, we are in our language here, we call them norms. So I think that's all for today. And I will stop the recording.